Welcome to our webinar, Strengthening Embedded Security in Late-Stage Development, Preparing for a Secure Production Phase. I'm Raphael Taubinger, Product Marketing Manager at IR, and I'm happy to introduce you to Tim Woodruff, General Manager for IR Embedded Security Solutions. As security threats grow more sophisticated, protecting your embedded systems has never been more crucial. Tim will dive into how you can fortify your projects with the critical security layers, even in late-stage development, ensuring compliance and safeguarding your products as they enter production. Let's get started. Tim, the stage is all yours.
Raphael, thank you very much for the great introduction.
So as part of a way of introduction, I think it is necessary I have to put a warning on this presentation. A lot of what I'm going to present in here is not about perfect security. So a lot of the security academics will talk about the need for these techniques to be improved. We have those already within IAR in terms of the products we do for security from inception. What I'm going to present here is a pragmatic solution for products that are largely already completed their development or already in production. So it is really around how do we add some form of security to existing developed products. So in terms of what I want to talk about this afternoon is the first thing is I want to talk about what embedded security is. Then secondly, what can happen if security is not taken seriously or it goes wrong, and then relate this back to the underlying legislation which is emerging. Then I will go on and talk about the techniques that can be used to improve the security of embedded products and why they are extremely difficult to use for products which are already in development or already in production. Then I will talk of some of the technical aspects of why building unique information for every device is so important, before I talk about the production systems that are required to produce that unique information for each device. I'll then talk about how we have integrated a lot of these techniques into what we do at IAR, before one of my colleagues will do a brief demonstration of the products in operation. And finally, I will close with a summary. Before I talk about security risks and implementations, I briefly want to mention what an embedded device is and what embedded security and cyber security is. So in essence, an embedded device is any product that has a computing capacity within it, whether this is using a microcontroller, a microprocessor, or something more powerful. The main thing is that it is executing software, and the execution of that software makes it particularly exposed to attacks to change the behavior of the device. So any device, whether it's connected or not, is classified as an embedded security device and is open to all of the attacks that I've mentioned previously. A connected device, or a device that could be called a cyber security device, refers to something with external connectivity. The demands on this device is much more basically prevalent because it can, and it is exposed to network-based attacks of that device itself. So within this, although we have basically two tiers, a lot of the techniques that we're talking about are equally as applicable to connected devices and cyber security devices, as well as standalone embedded devices. So what can happen if security isn't taken seriously? Well, there's four types of actions that can happen. Okay, the first one is that the company that produced the original device loses sales or revenue. So this can be basically performed by either enabling functionality within the device that was never authorized, or more importantly is that clones of the product are generated by copying the exact contents of the microcontrollers and microprocessors memory, or during production units are overproduced. The next threat is that basically the IP is removed from the device. So what this means is that people can read out from the memory basically some of the contents and then reverse engineer the contents of that memory in order to provide a competing product to the original company. The third one is that the device can then leak customer data if it is not protected, which not only puts the original company at risk, but also the users of their products. So the fourth way is that the device can be taken control of by an attacker in order to provide a different functionality to the way it was intended to operate. So what is the impact these things have on the business? The first thing is monetary loss or penalty, because cloned devices are produced, the IP is extracted, and therefore inferior copies could also be produced, which impact the reputation of the customer. So overall, wiping off the significant amount of the development effort that was basically invested on the basis of potential revenue. This next one is potentially compromised customers and dissatisfied customers. We've all heard about leaks of basically information, okay, and this is where basically customers are compromised. The next one is the ability to create national crime, where devices are taken control of as part of a wider crime to basically subvert the use of national infrastructures. All of these, though, add up to a potential ruin of reputation, trust, and potential even worse for the business in terms of the survivability of that business. Due to the risk of the information contained within these devices leaking and customers being compromised, and also the possibility of the use of these devices for creating greater national crime, it is not really surprising that the legislators in the world are basically coming up with restrictions on how these devices should be produced, consumed, and basically used during their life. So the legislation is emerging from the major areas of the world, whether this is from the US, the EU, or the UK. However, all of the techniques are basically based upon what's known as the 13 best practices, which have been developed by the IOTSF. And each of those bits of legislation is in a different state of maturity. The US and the UK has already passed the legislation, and the EU we expect to basically publish their legislation later on this year. For failure to basically meet some of this legislation by a device manufacturer can result in significant fines and enforcements by the necessary legislators. So knowing these risks to the product, how does a developer traditionally go about improving the security of the device? Well, there's a number of known techniques about how to improve the security of the devices. The first one, and is probably the most fundamental one that people can do, is to switch on the security of an existing device. So there's many devices out there in the market in terms of microcontrollers which have had security functionality built into them for a number of years. And these have generally not been switched on because there was seen as no need to actually switch this functionality on. The second technique is to add what is called a secondary secure element to the design, which is specifically there for storing the identity and proving the authenticity of a lot of the software that's running on that device. The third technique is the ability to add what's known as a secure bootloader to the product, and with that accessing data and keys which are used by that boot manager within a secure vault. The last one is generally not a technique that's talked about a lot, but is the first element, okay, of protecting any device. And that's basically the ability to disable the logging and debug ports of a product, and potentially by doing that through password protection mechanisms. So all of these techniques are excellent for products which are being designed from scratch. However, they come at a cost. Firstly, they will potentially require the relayout of the main electronics and the PCB, requiring a redesign of potentially an existing running product. Secondly, there will be the cost of integrating these new components and new software components into an existing running software design. There is also then the necessity in production to enable the functionality. And all of these items come with a potential impact on the memory usage within the system, and also the performance of the system, specifically the power on time of the product. All of those added together would result in a recertification cost of the product, which in total adds up to time, money, and cost. So security from inception products is exactly what IAR have been developing for the last 7+ years. However, in talking to customers, when we have sold these very advanced products, one of the comments that keeps coming back is, it's great for new designs, but hang on, I've got all of these products that are either in production or I'm going to take over 2 years to get these products ready for production. So please, can you add something that enables me to add some security to an existing design or a product which is in design at the moment? That then puts certain restrictions on what we can and cannot do. Okay, it means that we have to reuse all of the existing hardware that is within an existing product. We wish to minimize the amount of software changes, which then has a knock-on case of minimizing the software recertification costs. However, the comment is that they can free up a small amount of memory in the product. So the next diagram shows the fact that, yes, this is a traditional flow of what goes on in a normal development from feasibility through to production. So in essence, rather than basically starting off of defining the new security requirements, we have to get involved after the software implementation is done or is largely complete, i.e. in the late stage of development. And the security request and the type of things we are being asked to do is basically prevent anti-cloning, i.e. the ability to just copy the image from one product to another. The ability to protect my IP such that when the product is inactive, nobody can actually get access and extract the IP from the device. I want to basically be able to give the device some form of identity so that I can then basically use it for cloud onboarding or communication with wider systems. I also want to basically protect my user data, so I need unique keys for that. I also need to inject keys within my product as well, so I can prove who I am communicating with. And finally, I want to generate some unique passwords. So those are the types of requests that we are being asked to put in terms of some form of late stage security development. So given these requests from the customer to add some form of security to existing products, what have we tried to do? So the first thing is to realize practically every microcontroller has some form of unique information within it that we can then bind to. So for example, a lot of these devices have device unique serial numbers that are programmed into them by the manufacturer, or they have what are known as physically unclonable functions, which is basically characteristics of some of the electronics devices within them which are random and different for each device. So that's part one. The next thing we've been doing is to basically developing a production system to further exploit that unique information. So use that information in essence to seed further information that can be programmed within the device. The production system is also used to basically lock down the debug port to prevent unauthorized access. The third technique is, once we've got that basic information, is we inject further entropy or further randomness into a device as part of production. Okay, and that information is stored within the flash's device. And lastly, all of that basically produced entropy and produced uniqueness is then used to basically protect sensitive information, okay, and also to basically add yet more identity information on there. So in essence, what we are doing in a production system is generating more unique data for each device that goes down a production system. And that is then bound to that device, okay, and is checked by a single call in a software library on PowerUp, which is something I'll talk about next. So how technically do we improve the security of an existing product? So what we see on the screen at the moment is what we have in an inherited product. So this is a microcontroller which has internally flash and RAM, and within the flash is both the main application. It has sensitive code which is potentially subject to IP theft, although that is stored in the clear. It has an amount of data, and then within RAM there is data, the heap and the stack. All of the normal things that we would expect to basically find in a typical software application today. So how do we improve the security? So the first stage is for the security officer to define the unique information they want provisioned in the device. So this is likely to be a bunch of keys and certificates required for communication. The fact that certain data has to be protected, executables have to be protected, and also there's potentially passwords and random number stored within the device as well. So this is the responsibility of the security officer. The second stage then is the software engineer needs to define space within their memory map for a number of other items. So the first thing is that they need to find space for where the unique provisioned information actually is going to reside in the flash. The second thing they need to do is to add a small amount of library space to actually decode that information. And the third part is to put something in RAM where potentially the information will be decrypted on power up and only stored in the clear while the product is operational and power is applied to that device. So how do we produce this? Well, first of all is that there is a unique hardware device anchor, whether this is the serial number or some form of entropy that exists within the device, which is different from each of the device. And the system then generates, or the production system generates, the information which the security officers asked to be provisioned, basically in a unique encrypted form for that device based off basically the unique serial information and trust anchor that has been read from the device, encrypting it and binding it to that device. So therefore, when a unit powers on, the first thing it has to do is the application makes a slight call or a small call into the security decoder, which then basically goes through and checks the authenticity and the integrity of the unique provisioned information, i.e. it belongs to that device. And finally, then it will basically decode the necessary encrypted data and place this in RAM for future use. Finally, during the operation of the application, it can query the security decoder library to pull bits of information out of it. So, for example, if it was basically the device was setting up some form of a communication using a TLS stack, it would pull out the certificate information to pass to the server, and then basically use some of the associated keys to encrypt part of the external communication. So I'll now give an overview about what actually has to happen in the production system to make this happen in reality. So the first thing is that basically the OEM's operation team acquires the silicon and passes it to a programming house as blank chips to be developed. The OEM development team then specify the credentials that they want basically provisioned into the device. So referring back to the previous stage, the list of keys, certificates, random numbers, passwords, etc., which are required within the device. This is then passed to basically the programming house, who basically use this information when a device is inserted into the production system. And the production system then sets up a dialogue with the device to basically build that unique information into every single device. It also, as part of the production system, basically programs the main executable software into the device as well. So upon completion, these basically devices are then passed back either to a contract manufacturer or to the original development organisation, who will mount those individual locked chips into existing products. So having talked about the theory about how we can add security to existing devices, I briefly want to talk about IAR's embedded security solutions. Originally, this was intended to offer a complete seamless approach from basically inception of a product to volume production and beyond. This was basically designed around two products, embedded trust, and then the transfer to the production system using secure deploy. And that is the solution, the best solution we offer in terms of security from inception. However, we have also added, and I'll talk a bit more about this in the next slide, the new product called IAR Embedded Secure IP, which in essence is our solution which can be used with secure deploy to basically enable late stage security. Underlying all of this though is really we are trying to achieve four things from a security point of view. The first thing is to enable our customers to authenticate any form of data they use before they use it. So to ensure that it is integrable and also it comes from a valid source, irrespective of whether this is executable software which resides in the device or it is information which comes in from a third-party server or third-party source. The second thing is around active IP protection, which is in essence is preventing of the IP from being removed from the device and it preventing it from basically lying around in the flash in the clear. We also support on some of the more advanced products the ability to do software updates and preventing of rollback of software to previous versions which may have within them known security vulnerabilities and then open up the device for basically further attackers to get in. And finally, and throughout this, is the prevention of copying of invalid clones by simply copying the memory from one device to another. But underpinning all of these four techniques is really around the creation of unique device information on a production line through secure deploy. And as I previously mentioned when I introduced myself, although a lot of these techniques are within our existing products, we're also now basically enabling solutions engineering so that our engineers who have developed these previous products are available to help and support our customers on their very specific security journeys that they are taking. So having talked about what IAR does generally, I'm now going to talk about IAR's solution for late stage security, which is called ESEC-IP. So what you see on the diagram here is the flow through the system. On the left hand side you have what happens on the OEM or the development site, and what you see on the right hand side is what happens on the production side. So in essence, on the development side, the primary focus is on the development of the tool we called Orbit. Orbit is responsible for assembling all of the information that is required to basically secure the device into one package. So that includes the likes of the main executable, operating system, sensitive data, then certificate templates, signing keys, okay, and keys that need to be injection. Plus, most importantly, the template and configuration script, which tells the production system how it should operate. So that is all bound into a package, which is ultimately sent to a volume production system. But this volume production system, and it is not to a single production system, it is bound to one specific production system. So only one production system can understand that information. So therefore, if the information is extracted, it is useless to anybody else. And that is where the IAR secure appliance and the blue box comes in. So once the OEM has generated the production package, which is bound uniquely to one of our blue HSMs, it is then transferred to basically the production side. So I now focus on the right hand side of the diagram of what happens on the production side once the OEM has produced the production package, which is bound to one security appliance within the production system. So these are then loaded onto one of the programming systems, whether this is a desktop provisioner with very low volume capability or a mass production facility which can produce thousands of devices off a reel in very short time. So the main thing is that when the device is then inserted into the programming system, the security appliance sets up a dialogue with the device. This is based upon the security configuration, the template and the script which has been transferred to it by the OEM. So this is used to pull out the critical information out of the device, get the device to generate additional information, and then to install the bound information to that device onto it, and ultimately, finally, locking the device down and disabling the debug ports. So on the previous slide, I talked about ESEC-IP and how it generically works. There are in actual fact 3 different variants of ESEC-IP, each with various different purposes in life, okay, and are used for very different solutions. So the first one is ESEC-IP Basic. This is intended to produce the bare minimum of functionality, which in essence is to enable the secure transfer to the production system by binding stuff to a security appliance only, and then only allowing a basic identity to be produced for that device, which can be later used for cloud onboarding. The next 2, standard and professional, are very similar in concept and the amount of information that they can generate as defined by the security officer. The differencing though in techniques is that One is using the library concept that I mentioned a few slides ago. So Professional uses the library concept, which means that it is very easy to integrate that into a product, and those libraries also provide the necessary cryptographic functions. The standard version, though, is very much designed to be used by those customers who already have products with cryptographic functions in them and don't need or don't want to use the underlying cryptographic library, which was part of the flow earlier on. So that, for a moment, concludes my part of this presentation. What I'm going to do is now hand over to one of my colleagues who will show some of the functionality of ESEC-IP. And then they will, following the demonstration, they will return to me for a summary.
So we've got basically 4 stages to the process we're going to go through today. The first stage is going to be the configuration. The second stage, the integration with our application. The third, the production package creation. And finally, the provisioning of the device. So if I start off, first of all, we need a configuration file. And this is where the Orbit tool comes in very handy to help us create that. We can use, from the command line, we can simply type a command that will generate for us a blank JSON file, which is in fact our configuration file. And if I bring up a version here, so this is a version I've actually gone through and edited myself. You can see that it's the same as the one in the example here. So I've set, for example, my target address. So this is the address within the flash that we are going to deploy our OPDS provision data structure to. I've also defined an obfuscation method. For this particular demonstration, I am using char20. And I've also defined a data block. So you can see the data block is just purely and simply encoded in base 64. And if we decode that, you can see it just simply has the text string making security simple. So this is the first process. We'll then use that configuration file to generate a header file. Now this header file is what we're going to use with our target user application. So it defines to the application where the location of the OPDS is. It defines which form of encryption we're using, and importantly, it also defines an access class. You can see if we go back to our previous version that we define an access class of 2. This is purely a number that's used. It's just a constant that we need. So if we move on. So I've got a sample application. Let me bring that up on the screen. As you can see, it's very, very straightforward and very simple. All this sample application is going to do is it's going to dump some memory for us. In fact, it's going to dump memory from an address that we've specified to our OX8100. We can show that working if you like, but first what I'd like to do is to simulate a brand new device. I'm going to erase all the memory in my device. We'll let that erase. Of course, I've picked a device that has a huge amount of flash memory, so it'll take it just a couple of moments to erase it all. There we go. If I just open up a serial terminal at the same time, we can now run our application. And we should see from the output, so the location where our OPDS is, we literally reset all to all Fs. So we can see it's a blank flash. Now, if I move back, the next stage is modifying the application to use the security library. So as you can see, there are 2 parts to this. The first is that we have to implement a couple of hardware functions for the HAL layer. So there are 2 particular functions we need. One is the unique identifier function, and the other is the CRC. Well, so both of these 2 functions will need to be implemented. In the evaluation version, we've actually provided a software version of the CRC, but for the source version, we allow customers to use the built-in hardware acceleration they may have on their device, which is what I'm using on this device. Next, I need to add my security libraries. So as you can see, I've added my security libraries and I've added some configuration to it. So if I go back to my target application, we can see that I now need to stop it running. I now add my security libraries. I will disable this version here, and I will add a version of the functions that already has the security in just for speed. So you can see that as the slides, I've added this. These are the 3 functions that we need to add. The initial function, it sets up and checks the security, which we can see in our example here to check the security. And then we need to retrieve the number of provisioned data items of the type we've asked for. These are data access block 1 as per our initial configuration. And then finally, we're going to retrieve those and print them and build the application. So if I rebuild the application, we'll let that build. So while that's running in the background, we need to go back to our orbit tool to produce our PPKG. I'm not going to run that on the screen because obviously it'll give away my OEM credentials. So you just have to accept that I'm running this in the background. The next stage is for us to launch SDP. I just launch that and I bring that onto the screen. At the same time, I will. So here's my demo. Let me load that up. You just have to wait a little while it reprograms the device. Again, because of the large size of the flash, this takes a little bit of time on this device. But if we were using a smaller device, it'd be much quicker. Right. So now we can see that our device has been programmed and we have a completely different output in our text. Instead of seeing a complete blank page of memory, we can see that the OPDS has now been programmed into memory. And we can also see that the text string that we encoded has been pulled out. Though it's, as you can see from the output from the memory above, that string does not appear anywhere in the character, so we can see it's been decoded. And again, we're just demonstrating that for the purposes of this demo. So you can see that nowhere at all in our memory map was that string. However, from the original data block, making security simple has transferred into the memory and is now being decoded. One of the other things we could do for anti-cloning is we could edit our serial number. So at the moment, the HAL serial number or unique identifier is provided here. If we were to modify that function, for example, if we provided a different memory address, we could rebuild the function, go back through the process again, and we'd see something similar to this. It would now say that security, our OPDS is corrupt because the data doesn't match the unique identifier.
So thank you very much for doing the demonstration. So in summary, what I've just talked about is a technique which is aimed at adding security to his existing products. It is not perfect security, and no one should go away from this presentation thinking it is basically perfect security, but it enables people with existing products to add an element of security to their existing product without a whole-scale redesign. It is the techniques that I've outlined is about creating device security block which is unique for every single device and is bound to that device. So therefore the information that is generated cannot be decoded or used by any other device, which is then used to basically protect the information within that device. So the techniques that we've just seen enables the injection of unique device identities and passwords. Passwords in particular are part of the legislation. It also enables protection of IP, such that when a device is not powered on, the IP is just not stored there in the flash, to enable somebody to come along and pull the flash contents of the flash out and reverse engineer the software. It also enables anti-cloning of the device, so meaning that the image cannot be just copied from one device to another, and then as a result of that, the device, basically the second clone device, powers up and operates efficiently. That is also related to the production control issues, such that someone on a production site cannot just run a few extra units for themselves personally. Okay, all of these though is a step toward meeting some of the legislation. Okay, as a result, some of these techniques can be extended to basically add with additional software the ability to authenticate the software, so using the key injected material to basically prepare software so its origin can be basically established. So thank you very much for your time today. If you require any further information, please could you contact sales.security@IAR, or can you basically please look at the IAR website. Thank you very much for your time today.